Hi folks, this video is the vocabulary for the gas standard. It's step 1. So let's go ahead and get rolling here. First term is temperature. So as you might remember from our discussion of the demonstrations, temperature is it's a measure of the average kinetic energy. I'm just going to put average KE for that, kinetic energy, or average speed of the particles of a gas. Alright, so when temperature goes up, what that basically means is when temperature goes up, particles move faster. So higher temperature means faster particles. And we saw this with our demonstration with the dye in the hot water spreading a heck of a lot faster than it did in the cold water. So particle models, if we're drawing particle models for this kind of stuff, we may end up with something like this. Okay, so there's my box, and here are the particles in the box. We'll make them green particles. So I may have two particles over here rolling around, and one way we could represent their motion would be using arrows. So these guys may have small arrows. So this may be a low temperature over here. And then if I had the same two particles over here and they were at a higher temperature, then we may have longer arrows at that point. So this would be a high temperature. And that is the standard abbreviation for temperature. We'll use T all the time. Okay, also related to temperature is absolute zero. Absolute zero is specifically 0 Kelvin. That's where the 0 for absolute zero comes in. 0 Kelvin. So 0 Kelvin is negative 273 degrees Celsius. So this guy is negative 273 degrees Celsius. That's awfully cold. It is the lowest temperature you can have, and actually you can't even reach it. And the reason you can't go any lower is because at this point all particle motion stops. There is no particle motion, so there can be no temperature below this. So all particle motion stops. And then that takes us to our conversion between the two. A later video will walk you through some examples of this, but the quick little equation that goes with this is Kelvin equals degrees Celsius plus 273. The Kelvin degree is exactly the same size as the Celsius degree. It's just 273 degrees offset. Okay, so we have a little bit of data we'll be looking at, presumably through this week, that will have this type of graph. So let me get this graph set up for you. Alright, so there's the axes set for this, and we may have volume on this axis, and this one may be 0, and it would be degrees Celsius. So this would be temperature in degrees Celsius. So we're going to construct a graph like this week. And you may end up with a graph that looks something like this. Switch me on over. It's a fairly shallow graph, but it heads all the way back down to this point on the negative side of temperature. And this point right here, this would be absolute zero. The volume goes to 0 at that temperature. Absolute 0. And so going negative volumes makes no sense. So the temperature can't go any lower than that. So absolute 0. Pressure. Typically we use the variable P for pressure. And we have a variety of units that we throw on pressure, which is talked about in the step 3 video on pressure. So let's get this up here and I'll get those conversion factors in here for you. So basically what's going on with pressure is the particles they move and push on their surroundings. And we call that push pressure. So all gases do this, liquids do this also. Our primary units we use in this are going to be the atmosphere is the main one, 1 ATM, that's atmosphere. But we also use millimeters of mercury, a fair amount. That's a very common chemistry pressure unit. A more common unit you might be familiar with would be PSI, so it's 14.7 PSI. And then a much less common unit is the kilopascal, so 101.3 kilopascals. These are all equal to each other. You can use them in a dimensional analysis setup. So this guy right here is the atmosphere. This is the element mercury here. So this is a millimeter of mercury. Literally, the air can hold up a column of mercury 760 millimeters tall. That's where it's coming from. Millimeter of mercury. PSI, I think you know, pounds per square inch. And this guy is the kilopascal. So it's a metric unit. Kilo is the prefix, and then pascal is the base unit. Alright. So our drawing might look something a little bit like this. Alright, so here's gas particles for us. And I'm going to put them close to the walls so we can see them hit the walls. So there's a collision with the wall, that's a push. And here would be another collision with the wall, that's a push. And then this would be an example of something that may have higher pressure. So, collide, collide. Arrows are a little bit longer. Maybe there's a few more particles in here. So, you have higher pressures when you have more pushes against the walls. Alright, atmospheric pressure. Atmospheric pressure is the pressure caused by the weight of the atmosphere above you. So this is, so it's gas, the atmosphere, it's doing this moving around and pushing on you, but there's a lot of it. So its weight overall is able to push rather substantially on you. So the pressure caused by the weight of the atmosphere above you. And give or take, we're talking about 50 miles of atmosphere. So the atmosphere on the small scale may not seem like much, but when you put 50 miles of it, it actually is rather substantial. And that's where that 14.7 psi comes from. Every square inch of your body is feeling 14.7 pounds pressure. Alright, and just a little thing here. As you go upwards in altitude, so if you increase your altitude, then there's less atmosphere above you, so you will decrease, so increase altitude, you will decrease the pressure. And that's responsible for altitude sickness. It causes other issues too. Cooking times are different as you go up. You need different gasoline mixtures in your vehicle as you get up too high. There's a bunch of things that happen with altitude. Alright, for our picture. So I got a circle here, and we're going to call this circle a balloon. And inside of the balloon, I'm going to put a fair number of particles in here. I'm not going to put their little motion arrows on them. There's just going to be too many of them. Be too crowded, be hard to see. So there's a whole bunch of gas particles in here. they're banging off the sides of the balloon, and they're pushing. On the outside, I'm going to go ahead and have air. So here's my air. And notice how the air molecules, or the air particles, are a lot spread further apart. That's a lower pressure. So I've got lower pressure out here. And I've got a higher pressure inside. So if your container is flexible like a balloon, when the pressure inside is higher, the balloon's actually going to get bigger. And as it gets bigger, the particles will spread out, and eventually the pressure inside will equal pressure outside, and it'll quit growing at that point. So whenever you see something changing shape and gases are involved, it's going to be a difference in pressure between the inside and the outside that is causing that to happen. Alright, one more term to do. That one is volume. So I know we know volume. So variable is V. And the volume is the amount of space a substance occupies. Alright, so for us, our main conversion is going to be 1,000 milliliters equals a liter. And just as a reminder for a gas, the particles of a gas, they spread out to fill up the container. Take up the whole volume of the container. So it makes one of the things that makes a gas much different than a liquid. Liquids, they take somewhat of the shape of the container, but they have a limited volume. Their volume can't expand, at least not much. Alright, so drawing's really easy. Here's my box, and my gas particles, however many of them I put in here, they're not going to sit over here, so you don't have your gas particles over here in this corner just kind of hanging out. That's not the way they behave. They're going to go ahead and spread out. It's going to be somewhat random as to where they're at in here, and of course they're moving. There we go. And we have gas spreading out to fill its container. Alright, so those are the vocabulary terms. That is step 1 for this particular unit. You should go on and watch the videos for step 2, 3, and 4. They'll have you working with some of these terms and doing some conversions. And when you're done with that, you should start practicing and work your way up towards the check-ins. The basic level assessment will be on Friday. Talk to you later.